voxet omnia, mihi sunt contraria, virginum colloquia, Suspirit, il me fit temir. O sodales ludite, vos quisitis dicite, mihi mesto partite, consulite per vostero tua pulcra facies me feclanti milies pectus abet glacies. All right, so we left it off on this piece of code right here, where we were adding something to a linked list, adding something to an arbitrary index in a linked list, and we identified several different corner cases. One where where the list was empty, and so we needed to create a new head. One where the list was not empty, but we still were inserting as the head, and so we needed to handle that one separately. But at this point, I'm going to ask everyone here, are these really two different corner cases here? If you are inserting into an empty list, where are you inserting it? At the beginning, at index what? 0, right? So the conditions are the same, right? Maybe we can collapse these two cases down into one. The conditions are going to be the same essentially, because is empty is just checking to see if the size is 0, and that's where we would end up putting it anyway. But what about the actual code here? Well, this line is exactly the same as this line. So the only difference here is this line. If I were to be able to repeat that up here, then I could collapse these down into one case. Does that cause a problem if the list is empty? What does this end up doing? We create a new node, then we set the new node to this list's head. But if the list is empty, what is this dot head? Null. Is there any problem with setting next to null? It's already null, right? So it's an unnecessary function call, but what I would argue is that it's much better to collapse this down into one case rather than and pay for the penalty of whatever this one extraneous function call requires, because it's going to lead to a lot cleaner code here. So I'm going to go ahead and change this so that the index checking is up here, right? And then go ahead and get rid of my comment there, and we can collapse that down to just one. Simpler code is generally better code. Even if it's slightly, in this case, I mean, we've already chosen to use Java here, so we're not, efficiency is not our number one priority. But this is, simple, better, simpler code, cleaner code, that is our priority, right? Okay, so does any of this actually work, right? So let's come over here to my list tests, and let's design at least one or maybe a couple of tests to actually make sure that this is working. Public void, linked list, add tests. All right, there we go. And let's go ahead and add a couple of things here. First of all, I need my linked list. Let's just go ahead and keep it simple, integers. New my linked list. Right, and let's go ahead and insert 10, 20, and 30. List.add element 10, 20, and 30. Now we've already looked at this from the perspective of the debugger, and I saw that 10, 20, and 30 got in there. But the whole point of doing unit tests is so that it's repeatable. Because if I come, and I've already done it, I've come back and I've changed things, right? I want to make sure that it's still repeatable, that these tests are repeatable, so I don't have to keep, running my debugger and then manually checking every single time. The way that I can do this is by creating a expected and actual, right? And if it's 10, 20, and 30, then it should be 10, 20, and 30 in the list. So let's go ahead and grab each one of those things and verify that it's what it should be. So my expected is going to be 10, and my actual ends up being list.getElement at the 0th index there. Right? And then let's assert that the expected is equal to the actual. Right? I would want to repeat that for the other two elements. Make sure that you're not just doing it for one element. Right? The expected on the second one would be 20, the third one would be 30, and this would be index 0, 1, and 2. Right? Let's run this again to make sure that it works. Right? Well, I guess this is the first. We've run this before, but 7 out of 7 works. Except that I don't have good code coverage here. Remember this tool right here? This will highlight things in red if it's actually being tested. It will, or in green if it's actually being tested, in red if it's not being tested. So let's run this again and look and see which one of those test cases is actually running. Right? So there's add element. It looks like everything was actually running. Right? That because I was always inserting it at the end. So the first one, when I inserted at that new node, that 10, that got tested, and then the rest of this also got tested. Right? Does that mean all green is, the only red here is that I'm not testing bounds. You can do that. That's just, we've done that before, right? But is that sufficient? Everything was green, good to go? In fact, I would encourage you to use this code coverage tool in your write-up as well. Because in your write-up, you have to you have to explain your testing, right? How many test cases? Why was that sufficient, right? Well, one thing that you can say is I ran a code we ran a code coverage tool was run, because you don't want to speak in first person, and the code coverage was 100% or something, right? Or something acceptable like 99%, right? And that's a justification for, hey, that was sufficient testing, right? This still is not enough for me, though. We tested one test case where we inserted into initially empty list by inserting 10, right? And then we were always adding it at the end. What if we were to repeat this test here, but then add 42 at the beginning again, right? So add test, insert, right? So what I'll do is I'll say list.add element, not at the end every single time, but let's add 42 at index 1, right? Actually, let's insert it at the beginning, because that's a corner case, right? Insert at start. There we go. Arguably, I don't need to repeat this, but since I copy pasted it, I'm going to keep it, right? What should it look like now? It should be 42, 10, 20, and 30. So my expected now for the first one is 42, 10, 20, and then we'll add on one more here to 30. Right? And make sure it's 0, 1, 2, and 3. Right? Does it still work? 8 out of 8. Yay, we got it. Right. What else would you want to test, though? You'd want to test inserting 42 right there, and inserting 42 right there, and inserting 2 where? Or 42 at the end. Right? This one was just at the start. If you wanted to repeat these tests, let's go ahead and do it for the end. Right? Start at end. All right, where would you end up inserting 42 at the end here? Oh, there is no this because I'm not in the context of the class, but I could manually just 3. Right? Just hard code it. Hard-coded values in testing are perfectly fine. Right? 42. So it should look like this now. Right? Change this back to 10. Change this back to 20, 30, and 42. And by the way, you could probably see a pattern here that you could probably write a loop to do this so that you're not cutting and pasting, right? Let's go ahead and run this now. Should be 9 out of 9. I ran it, right? Come on. 9 out of 9. Come on. It's already running. Oh, wow. Is it, there's no way that's an infinite loop. Is there? All right. I don't know why it says it's already running, but it's not. I don't buy it. There's something. It just got hung up or something. All right. Let's go back. Oh, that's console. Come on. All right. There. Finally. Just needed to get kicked in there. All right. Come on. All right. Now it's going to register all those clicks that I had. So let's go ahead and just terminate them all. It's my computer is almost 10 years old now, and it's still kicking along. But OBS, QuickTime, Eclipse, all that stuff all together, it's just too much for it. I'm gonna have to ask for a new computer. All right. This is I think that this is an i9. i9 versus M4s. Which one's better? M4. M4 is better than i9? Okay. Then I'll get an M5. All right, so that's pretty good. Come on. All right, the other problem is that I'm it's drained all my power, so it's actually throttling. That's probably the biggest issue here. Come on, there we go. All right, so let's come back up here. What else do we need to do now? We already did get element. In fact, we were testing that. What about replace element here? So let's outline that. Remember, the idea here is that we need to go to the indexed element. We're going to take that thing out and return it, but then replace it with X. So what's the very first thing that I should do that I'm going to let you do as an exercise? Yep, so bounds check. Bounds check. Right? I'll let you do that. Right? Otherwise, we need to find that element. Guess what we did already? Come on. Get node at that particular index. There we go. And, oh man, this is slowing everything down. Node T, I'll call it current, right? Or just call it node or something like that, right? And what I need to do now is I need to get the element stored there, right? So because I'm going to return it, it's an element of type T. I can't call it X. I'll call it old value. That is equal to current.get element. Right? And eventually I'm going to return that. So return, wow, return old value. There we go. All right, and what do I need to do now to replace it? Come on. Current dot, it'd be nice if I could just set element to X, right? Element. There we go. Except that I don't have a setter here because I never designed it that way because I prefer immutable objects. But now you have a reason, a very good reason, to redesign your node class, to open it up a little bit. And we already did setters for next. We might as well do setters for element now that I have a reason to do so. Let's go up to source. Oh, man. Come on. OBS isn't crashing at least. Generate. There we go. Or maybe it is. No, no drop frames yet. All right, so there we go. All right, so save that and come back over here, and I think that we're good. I won't bother writing tests for that because you can write the tests. We've seen the pattern already. You put stuff in, you perform the operation, you see if that operation worked or not. What about remove element? How are we going to do that one? Well, as with all design, you should start with whiteboarding first. Come on. All right. So let's think about what that looks like. All right. So if I have an element 10, oh wow, hopefully this actually works. 20 and 30. There we go. And we'll just say that it looks like this. Let's think about, well, we're always going to be wanting to think about corner cases, but let's think about the general case here. Suppose that I wanted to delete at index 1. At index 1. Remember that these are the indices 0, 1, and 2. Okay? Come on. There we go. All right. So that means that I want to remove the middle node right here. All right? You know what? Let me get a different. So I never bought the idea that USB-Cs or Apple's USB-Cs were any different than like a crappy $8 one that you could buy off the shelf, but it is definitely true. All right. There we go. And I think that there was like a, not Mythbusters, but who's that guy? The Mythbuster guy? Adam Savage. He did a video once where they actually took it apart, and yeah, it's way more. The actual USB-Cs that come from Apple are way more complicated, and they're much higher power and better. So hopefully that works. Hey, all right, there we go. So now I'm actually powering off of an actual Apple USB-C here. All right. So you get what you pay for. Right? Anyway, so we want to delete this guy right in the middle here. What is it going to look like after we're done? Instead of this node pointing to the node that we want to delete here, where should it be pointing to? That one. In other words, we're just going to circumvent this node entirely, right? Now, if you think about pulling the chain taut, right, then this guy might be hanging, dangling off at the bottom or something, but that doesn't matter because it's Java. Java will automatically clean that up for us. If this were a C or C++ implementation, yeah, I would definitely have to sever that connection there, and I would have to clean up this node, free it up, or delete it, or something like that, right? But ultimately, you know, if it's in the middle here, we need to, 1, find the node. That sounds familiar. We've done that now several times. That's why we put it into a function. 2, make the previous point or refer to nodes next. Right? So if I'm going to give these labels here, say previous, current, and next. All I need to do is make sure that previous is now pointing to next. Right? So as a first step here, let's find not just the node, this one single node here. Let's find all 3 of these so that we can do everything in terms of all 3 of them. Right? A little bit better. Not great, but all right. And again, what's the first thing I should have done? 0, to do, bounds check. Right? Otherwise, let's find those 3 nodes. Find the 3 nodes. Right? So the previous is going to be this dot get node at index, and it's going to be at index -1. Right? And I'll label that as previous, right, is equal to. Repeat that for current and next. Current and next. Except that's going to be at index -1 and +1. Now we discussed that I probably shouldn't be doing that 3 times. If there are a million elements in there, that first line on line 58, it performs 1,000,000 times. Then on line 59, we perform it another 1,000,000 times. Line 60, we perform it another 1,000,000 times, 3,000,000 times. If I'm already at the previous, how do I get the next? Yep, previous dot get next. If I'm already at the current, how do I get the next? Current dot get next. Right. And I've cut 3,000,000 operations down into 1,000,000 operations. Right. Good. Ultimately, I'm going to return the occurrence value, so return current dot get element. That's why I wanted to grab it in a node, because I want to at least get that value to return it. And now all I need to do is make the previous point to the next. Make previous point to next. So previous dot set next to next. That's it. I'm just circumventing that node right in the middle. Right? All right, we're not going to test it, but I'll leave the writing test to you. Is there a corner case that we should think about here? Right? The one that I designed this for was the general case where we're removing from somewhere in the middle, where we have a previous and we have a next. Let's think about other corner cases here. What if it's 10, 20, and 30, and that's the end? What if we wanted to remove that one? All right? Now apply the same logic that we just did. What would you end up doing? This is the previous, this is the next, or sorry, this is the current, and this is the next. Is it okay for next to be null? Yeah, so far. Now when I circumvent this, is it okay to do that? Set the previous nodes equal to the next, which is null. Right, what will that end up doing? That'll just end up shortening the list, and you don't have this guy anymore. Right? Okay. Oh, by the way, there's one thing that I did forget accidentally. Right? What else should we be doing before we return? If we're removing an element. Size minus minus. Right? That's going to be for all cases there. Okay. All right, so that corner case doesn't actually look like it's any different from the general case. But there's another corner case here that we need to consider. What if I remove this one? Right? So can I get the previous, the current, and then the next in this case? Nope. Because there is no previous. So if I tried to circumvent that by doing this, I'm going to get a null pointer exception here. Right? So this is one very special case where we're removing from the head of the list. Right? So let me go ahead and create if the index is equal to 0, then we'd have to treat that separately. Else. There we go. And let's move all of that in there. Okay. How am I going to do that? What should it look like? Again, let's whiteboard this. What should it look like in the end? Remember that this is head. Right? You want to remove the head. What would it look like? Sever that connection and make head point to the next node. Head.next. Right? So this dot head is equal to this dot head dot get next. That's it. This dot size minus minus, of course. Right? And then return the old value. Ah, darn it. The old value. I've lost reference to it already. So I should have saved that off. T, old value, is equal to this dot head dot get element. And then I can return that old value there. Okay? We have some repeated code here. Minus minus. I'm returning a value that I'm getting from somewhere, et cetera, et cetera. But I would argue in this case that it's kind of necessary. Like, could I move this size minus minus down here? No, the compiler won't even let me do that. Why? Because I'm already returning here and I'm already returning here. I would have to restructure this code significantly and substantially in order to get rid of those two lines. And in the end of the day, it probably would actually be a little bit more complicated because I need to get the old value from the head versus I need to get the old value from this current. Right? So that's going to be an if-else condition. And then I've got some common code, and then another if-else condition, and then some more common code. Sometimes it's okay to repeat yourself. Right? It's if the alternative is more code, more complex code, then yeah, go ahead and repeat yourself. Right? And there, we're done. Right? At least we did the basic CRUD: create, retrieve, update, and destroy for a linked list. We didn't test everything, but I'll leave that to you when you eventually design your own sorted list ADT by the end of the course. All right. What I want to do is I want to draw your attention to alternatives or variations on this theme. Let me go ahead and go to my drive, and where's the lists? There we go. All right, so here's the traditional linked list once it gets pulled up here. There we go. Come on. There. All right. Here is the traditional simple linked list holding 3 elements here. Zoom in on that, right? Where you can only go one direction. Well, what if you want to go the other direction, right? Then that's where this comes in. It's a doubly linked list, right? Where you not only have a reference to the next, but each node has a reference to the previous. That way you can go back and forth and back and forth. You could start at the end as well. You can keep track of the head and the tail, and then you could start at the end and go traverse back to the beginning, right? Or you could go start at the beginning, traverse to the end, right? And at either endpoint are those sentinel nodes, those sentinel values of null, to indicate that those are the endpoints of the list. This is called a doubly linked list, right? You can also have, there we go, a circularly linked list. Right? So we have a defined head because we have to start somewhere. But instead of pointing to a sentinel value at the end, it wraps around to the beginning. Right? This could be a useful data structure if you have a bunch of stuff that you're going around in a circle and processing it continuously. For example, have you ever heard of a token ring network? All right, no, it's way before your time. We all have now routers, right? If you want to plug into a network, you have a router, and then you can plug all the computers into it, and it takes care of everything for you. Back in the day, you had a token ring network where you had this, it looked more like a coax cord, right? And then you physically had a cord to the next computer. Then you had another cord to the next computer, and another cord to the next computer, and then the last cord went back to the beginning of the computer, because it was a token ring, right? What happened is that each person on that network, on that token ring network, they got their own slice of data, right? So they could send a packet to everybody, and then the next computer got to talk, then the next computer got to talk, etc. And even though token ring networks are not a thing anymore, this data structure, this approach can be useful in a lot of use cases, right? And it's called a circularly linked list. You can even have what are called skip lists. Come on. iDrive is slow still. All right, there we go. So what you have here is you have multiple ways of getting to places. With the regular linked list, one node goes to one node, goes to one node, goes to one node. This is kind of like a train system, right? Where if you went from one train station to the next train station to the next train station, in other words, you stopped at every location, like in the bottom here, right? Those are called locals, right? And these are called, does anybody know what the opposite of locals are? What? Not globals in the context of a subway system. A subway system, I don't want to have to stop at every damn location. I want to expressly go, right? That's the express, right? You can skip all the locals so that you can go from one major train station to another major train station, right? In other words, faster. So instead of having 3 stops or 3 operations to get to this guy right here, right? You can just use this to jump to that location immediately, right? It's kind of a compromise between an array-based list that offers you immediate access to an ith location by jumping there using random access, versus a linked list, right? And depending on how many expresses you design into this, right, it can actually get more complicated than either one of them, because if you add every single location, right, from any station I can get to any other station, right? Now it's quadratic. There's a quadratic blow up of the number of connections. So you want like a middle ground there somewhere. Right? That's a skip list. And another compromise is called an unrolled list. Right? Here it is. Instead of a node holding just one element, it can hold m elements, where m is some configurable value, 10, 20, 30 or something. The head will refer to that node, which is an array, and then it has a next to another array, and then a next to another array, right? And then what you can do is you can fine-tune this m so that you can minimize cache misses, right? If your cache is like, say, one kilobyte, then you could load up the entire, like a whole 1 kilobyte into that cache at a time, and then you won't have any misses here at all. And then you can load up the next one and the next one and the next one. Again, this is kind of a hybrid in between a linked list and an array-based list. It's got arrays, but it's not one big giant array. So it's a compromise between those two things. Unrolled, skip lists, circular, doubly linked lists, and just regular old linked lists, right? All right, so I usually I put those in the notes, but oh no, where are my notes? There we go, here it is. Variations, all right? So again, variation, I'll just go ahead and cut and paste this and then go over it again, I guess, all right? You can have a tail and a previous reference to make it a doubly linked list. The advantage here is that you can traverse in both directions. The disadvantage is that it's twice as complex to implement. If you're going to insert something now, you need to take care of the next, and the previous, and the previous. So there are 4 things to worry about now. Circularly linked lists, the tail points back to the head. Token ring network, for example, or any circular data structures where no, you need to go around and around and around and around until they're all processed or something, right? Unrolled linked lists, where each is an array. You can also have skip lists, which is a linked list, but some random access, keeping track of several next stops, right? Local versus express, right? This is a local train versus express trains. Right. We don't have a lot of trains around here, so maybe it's difficult to think in those terms, right? But you always want to get on the express. You usually take the express and then, oh no, my next is 3 stops away. So I'll get off, take a local, and then get to the exact location that I want to get to. Right? All right. Any questions on linked lists and all that stuff? No? Then let's go ahead and have some applications of these things. We've seen these things before. They're called stacks, right? Stacks are what are referred to as restricted access data structures, right? The things that we've looked at so far, lists, sets, etc., maps, they are unstructured. They just hold stuff, either in a key value pair, in order with a link with a list, or in some bag in unordered like sets, right? However, you can impose an ordering on stuff by, say, lists, by sorting them, right? You rearrange the the elements in that list until they're in order. That's imposing an order on the data structure's state. The alternative is to create a structure where you impose ordering on the behavior instead. In other words, you restrict access through its public interface so that you can only do certain things, right? A stack does this with 2 basic operations. Right. Do you remember what the basic operations for stacks are? What they're called and why they're called that? Push and pop, right? And I'm 99% positive that they come from cafeteria plates, right? That mechanism, they still have them in like, where's everybody is the Cather the best place to eat or not? Cather or Selleck, or what's the best place to eat now? Selleck is still the best? Okay. Okay. They still have plates there, right? And they still have this mechanism where you push down the plate to get it into the spring-loaded mechanism, and then these little tabs hold it in, and you pop it off. Oh, it doesn't. They don't have these things anymore?
No, they have like little plastic crates you get.
Plastic crates. What do those look like?
They're called like I don't know what they is. Yeah, the Aussies.
Aussies?
They're these like green or clear crates that once you're done, you throw them in like a recycling bin. They reuse them.
Oh, okay.
Kind of like a Tupperware.
Okay. All right. Aussies, they're called?
Yep.
Weird. All right. Anyway, maybe they don't exist. I've seen in plenty of places still in cafeterias where you push down the plates and then you pop them off the top, right? And again, pushing is just adding it onto the top of the stack, right? And again, there's no top. That's why I'm saying top in quotation marks there, because it's in a computer. You turn your computer upside down. You're not gonna, ruin the plates or anything like that. And then a pop is to remove and return the top element on the stack, Okay. If I restrict the strict attention to just these two operations, that's how I've imposed order. There's no way that you can sort it, right? You're not imposing an order on the state. You're imposing an order on the behavior, how you interact with it. Okay. You can't go just down to the bottom of the stack and take out a dish. You can't go into the middle and take out a dish or anything like that. And for that reason, stacks are LIFO data structures. The last one in is the first one out, right? And again, this is ensured through the publicly available interface. You're generally not allowed to insert arbitrary objects wherever you want or remove arbitrary objects from wherever you want. All right, let's talk about implementation. Implementation, right? How? So let me come over here and let's get rid of all this stuff. And let's go ahead and create a new class called myStack. And it'll hold elements of type T. All right. How do you want to implement this? Well, first of all, before we talk about implementation, let's design the interface. Public T pop, right? And it'll return a value. Public void push, and it'll take a value X and adds it onto the top of the stack. Adds the given element code X to the top of this stack. Right? And what would pop do? Removes and returns the element at the top of this stack. Right? There we go. All right. I can't implement them yet because I don't have a way of representing my stack yet. How do you want to do it? I could do it as an array, right? Or I could do it as, I could do a hash map, right? Although I'm not sure what the keys and the values would be, like what that relationship is not necessarily clear to me. Right? I could represent it as a linked list, right? We just went to a whole bunch of trouble to design an array-based list and a linked list. Why don't we reuse it, right? So you could do my array list of elements of type T, underlying list, right? And I'll make it private. Now, if I did that, what does the pop look like here? Well, let's try push first then. Underlying list, dot add element, where? At the end? There, that's it. What about pop then? So in other words, the end of my list, that's going to be at the top of my stack. Here's my list. All you have to do is rotate it like this, and now this is the top. The end of the list is the top. Right? So underlying list dot remove element from where? And return it. Yep. Underlying list dot get size. There we go. So simple. What is this called, by the way? This is the power of composition. My stack is composed of an array-based list under the hood here, right? And that's a great implementation. I'm reusing it. This is just what's called a thin wrapper around another data structure that restricts access to only working at the end of the list. You can put stuff in there, you can take stuff out, but you can't do anything else, right? And that's how I get my stack out of this. At this point, let's go ahead and make it a little bit better. It can be any type of list. Sometimes it could be a linked list. Sometimes it could be an array list, right? And we'll have to redesign it over here. And let's go ahead and grab this here, import this. There we go. And the underlying list, now that I'm using Java's list, is dot remove element. Hey, remove last. Nice, right? And underlying list dot add last X. It's almost like they were thinking about using these things as stacks. And in fact, they were. There is no stack implementation. I don't believe that there's a stack implementation. They want you to use the list as a stack. right? Well, it's still not going to work here because I haven't created a constructor. So public, my stack, right? And what we'll do is we'll say this dot underline list. Which implementation do we want now? Do we want an array list? Or do we want a linked list? We designed and implemented our own, but at the end of the day, we should be using the ones that are built into Java. In your last assignment, when you're asked to implement your own, don't use those. That's big time points off, right? Because we actually want to see your own implementation. But which one should we use here? A linked list? Why did you jump immediately to a linked list?
It seems more similar to a stack.
Yeah, because you're always deleting this node and adding another node and linking it, and it's at the end, and it keeps track of the tail, so that's efficient, right? What would be bad about using not necessarily bad about using an array list, but what's one drawback? You fill it up. What happens now? You're copying everything over. Right? You don't have to do that with a linked list, right? You fill it up, and ultimately what you have to do is you have to copy it over to make an array bigger to hold it, right? And in case you're wondering how these are actually implemented, guess what? They're implemented exactly how we implemented them. Right? Let's go to an array list. Let's go all the way to the top here. What's it? There it is. Element data. What's it holding it in? An object array, right? And is there a? Yep, we're creating it with initial capacity here. We'd have to find out where it is in here, but there's trim to size. That's shrinking it. Increasing the size. Ensure capacity. That's up public. There we go. It's called grow, right? That's exactly what we did. It's just they're doing it a little bit more sophisticated here, right? How big a minimum growth would be? The minimum capacity minus the old capacity. The preferred growth. Ooh, that's a good one. What is that doing, by the way? What is this operation right here? This greater than. It's a bit shift. So if it were, say, 4 before, what is it going to be now? It doubles it. A bit shift multiplies by 2. If it were 8 before, what is it now? 16. In other words, it's growing exponentially, right? And then you've got a bunch of other stuff here, right? Linked lists. How are they representing a linked list? As a node, right? And what does their node class look like? Right? Jump up here, all the way to the top. Right? Theirs is much more sophisticated, but whatever, right? First, last, this is a linked list node, right? No, I want the actual node. The node class. There we go. Okay, so it's a private class inside. It's holding what? An item, and it's holding a reference to a next and a previous. What kind of linked list did they actually implement then? A doubly linked list. You can go forward and backwards, right? All right, so let's get rid of that. Right? We decided on a linked list here. Right? Let's see it in action. Public, static, void, main, string, args. Right? So let's go ahead and create a my stack of, say, integers. Is equal to new my stack. Don't call things my, right? And I'll call this stack for short. Right? Stack dot push 10, push 20, 30. Right? And note here that stack, that's the only thing available to me, right? I can only push and pop. I've restricted access. That's how I've imposed a structure on this data structure. That's why we call them data structures, by the way, right? Structure means that it's something that you can exploit for efficiency, right? If I were to pop, what would you expect at first? Yeah, I meant to do 10, 20, 30, but we'll go ahead and go with that stack, right? So 40, 10, there we go. What would you expect the output here to be now? 40, 30, and 10. And it looks like it is. Good. What would you expect the output to be now if I try to pop 4 things? Is there a 4th thing to pop? No. Exception? Linked list remove last. What the hell does that have to do with a stack? Right? Remember that this is what we call a leaky abstraction. Right? So let's improve our implementation here. If you were to try to push up to pop off of an empty stack, what should happen? If this dot underlying list dot is empty. Ooh, that looks nice and familiar. Right? If it's empty, what should happen? We could throw our own exception, right? Throw new runtime exception. You cannot pop from an empty stack. Noob. Right. Noob. There we go. Right. Or what else? What's an alternative? We could return some flag value to indicate that you shouldn't have asked for that. I asked for something that doesn't exist, so I'll give you something that doesn't exist. Right? Null. Right? And now let's see what the consequences of that are. Just null. However, how would I distinguish between whether or not I actually pushed null onto the stack? For example, this is going to have the same exact output. Not the same exact output. Let's move it so that it is. Same exact output, but completely different reasons. This one is because I explicitly pushed null onto the stack. It's not an error. So how would you distinguish between those two things? You could give yourself access to a question. Is empty. Right? Return this dot underline list dot is empty. And that's why we call this what's called a thin wrapper. If you have an object here that like a list, a linked list in this case, and you wrap it around another object through composition, it's kind of a thin wrapper. I'm going to do everything in terms of the underlying data structure and reuse its functionality. Right? To return is empty here, Boolean, right? All I'm going to do is say, is the underlying list empty? And then you can ask yourself over here, right? Is it empty? If is stack dot is empty, then what I pull out from this is actually null, right? Versus no, that was because it was empty, right? Okay. And that actually means that I can put this into a loop while it is not empty. Nice. I can just go ahead and pop, pop, pop instead of hard coding those values while stack dot is not empty. While the stack is not empty. Right? And now 40, 30, 10. Right? Is there any other bells and whistles that we would want? What's the opposite of being empty? Full is full. What does that mean for our implementation though? That we'd also want to keep track of. I mean, is there a maximum capacity of a linked list? Nope. So in this particular implementation or in this particular implementation or design, I'm thinking that there should be a max capacity. Right? And maybe the default here is 100. Whatever you want to do. Maybe instead you take that in as a constructor. Int max capacity. Right? And this dot max capacity equals max capacity. Right? There we go. And this one should be what? I don't want to repeat myself, so I'll say this 100. And then I won't assign it right there. Right? Now that has implications for the rest of this stuff, right? Is full would be this dot underline list dot size equal to this dot capacity, max capacity. Return that. That means it's full, right? What does it mean for pushing on top of a full stack? If this dot is full, what would you do now? What are some options? throw an exception. Right? 2, there's not a return value here, right? So there's nothing to return here, but what's another option here? When you don't know what to do, but do nothing, exactly. It's a nope, no operation. There we go. So it all depends on how you want to use it, okay? So lots of options here, right? And in fact, if you look at the implementations we'll look at the implementation for Java at the end, and you'll see that all of these options are available to you. It just depends on how you use it, right? So whether or not you are throwing an exception, returning a flag value, or doing nothing, right? Well, maybe I want to do all of those things, right? Or I want to give whoever's using this the capacity to do all those things, right? But otherwise, there's your stack implementation. It's nothing more than a thin wrapper around another data structure. DRY, don't repeat yourself. If you have a nice implementation of a list already, reuse it as a stack, right? All right, what's the other cousin of a stack? Heaps, we'll get to those eventually. But A, Q. How do you think that's going to work? We'll do it on Friday. Exact same thing, except that we're working from both ends, right? All right, I'll see you on Friday, where we'll be in the Elite 8, right?